In today's class, we are going to discuss about the experimental observations of photoelectric effect. Means, we are going to discuss about the observations of photoelectric effect experiment. So, here already we know that what is the experimental setup for the photoelectric effect. The experimental setup consists of evacuated glass tube with a side tube, and this side tube is fitted with a quartz window. It is a quartz window. The quartz window permits the which radiations? UV radiations. Glass window permits the visible light. Then it is called cathode and it is called anode. Then cathode is connected to negative terminal of the battery, and anode is connected to positive terminal of the battery, and there is a micrometer is used in the circuit that can be used to measure the photocurrent produced in the circuit, and voltmeter is connected. That voltmeter can be used to measure the potential difference applied across the cathode and anode. So even though potential difference is applied across the cathode and anode, but there is no current in the circuit because there is no ejection of electrons from the emitter plate. Cathode is called emitter plate. What do you mean by emitter plate here? The plate which can emit the electrons when the light incident on it. Cathode is also called emitter plate. And these ejected electrons are collected by the anode. That is why anode is called collector plate. So listen here once again. When the electrons are ejected out from the cathode, those electrons are collected by the anode. Then that is why the anode is called collector plate. Why the anode collects the ejected electrons from the cathode? Because anode is at positive potential. There is a force of attraction between the ejected electrons and the potential of the anode. What is the potential of the anode? That is positive. Then there is a force of attraction between negative and positive. Then when the UV radiation fall on the cathode, the electron is ejected out from the cathode. For example, let us take zinc. In case of zinc, for the ejection of electron, which type of radiation is required? That is a UV radiation. If we are going to use cesium metal, instead of zinc here, I will use cesium metal. So we have to incident which type of light? That is a visible light. Means if we are going to incident the visible light on the cathode, the window must be glass. Okay. So because glass window permits the visible light, quartz window permits the UV radiation. Then, so as this electron is received by the anode, then there is a current in the circuit. That current can be read by micrometer. Okay. And what is the potential difference applied across the cathode and anode? That can be measured by voltmeter. Then what are the observations here? What are the observations of the experiment on photoelectric effect? First observation is that observations. These are the experimental observations. Experimental observations on photoelectric effect. So first observation is that effect of intensity of incident radiation. Intensity of incident radiation. Incident radiation on photocurrent. Photocurrent is also called photoelectric current. So what do you mean by photoelectric current or photocurrent? It is current produced due to the ejected electrons from the emitter plate. Okay. So those electrons are called photoelectrons. The current produced due to the photoelectrons is called photocurrent. Then how this photocurrent depends on intensity of incident radiation. Intensity of incident radiation. See here, this is a UV ray or UV radiation. Now let us consider, if the frequency of incident radiation is greater than threshold frequency, then only there is a ejection of electron from the cathode will be takes place. So now when light incident ಮಾಡಿರ್ತೀವಲ್ರಿ ಅಂದ್ರೆ ರೇಡಿಯೇಷನ್ ಇನ್ಸಿಡೆಂಟ್ ಮಾಡಿರ್ತೀವಲ್ಲ ಅದ್ರ ಫ್ರೀಕ್ವೆನ್ಸಿ ಥ್ರೆಶೋಲ್ಡ್ ಫ್ರೀಕ್ವೆನ್ಸಿಗಿಂತ ಹೆಚ್ಚಾಗಿತ್ತಂದ್ರೆ ಕ್ಯಾಥೋಡ್ಲಿಂದ ಎಲೆಕ್ಟ್ರಾನ್ ಇಜೆಕ್ಟ್ ಆಗಿ ಹೊರಗಡೆ ಬರುತ್ತೆ. ಓಕೆ, ಸೊ ಅಂದ್ರೆ ಕಂಡೀಷನ್ ಏನು ರೀ, ದಿ ಫ್ರೀಕ್ವೆನ್ಸಿ ಆಫ್ ಇನ್ಸಿಡೆಂಟ್ ರೇಡಿಯೇಷನ್ ಮಸ್ಟ್ ಬಿ ಗ್ರೇಟರ್ ದ್ಯಾನ್ ಥ್ರೆಶೋಲ್ಡ್ ಫ್ರೀಕ್ವೆನ್ಸಿ, ದೆನ್ ಓನ್ಲಿ ದಿ ಎಲೆಕ್ಟ್ರಾನ್ ಇಜೆಕ್ಟೆಡ್ ಔಟ್ ಫ್ರಮ್ ದಿ cathode here. Then what is the minimum frequency required to eject the electron from zinc here? That is about 1.044 into 10 to the power of 15 hertz. It is the minimum frequency required to eject the electron from the zinc metal. Then in terms of 10 to the power of 14 we can write 10.44 into 10 to the power of 14 hertz. Then it is the frequency of which radiation? UV radiation. So here the frequency of incident radiation must be greater than this frequency, then only there is a ejection of electron from the zinc plate takes place. As the intensity of incident radiation increases, as the intensity of incident radiation increases, as the intensity of incident radiation increases, the number of electrons emitted per second also increases. The number of electrons emitted per second also increases. So if the number of electrons emitted per second increases, then the photocurrent increases. See here, what is the formula for current? That is charge per time. As the charge increases, current also increases. How to increase the charge? By increasing the number of electrons, because we know that Q is nothing but N into E divided by T. As the number of ejected electrons increases, then the current also increases. How to increase the number of ejected electrons here? By increasing the intensity of incident radiation also increases. Hence the photocurrent is directly proportional to intensity of incident radiation. Directly proportional to intensity of incident radiation. Intensity of incident radiation. This is very important. How to increase the photocurrent here? By increasing the intensity of incident radiation. Then how to increase the intensity of incident radiation? So by increasing the power rating of source of light. Let us take it is the source of light. S will be the source of light. For example, I will increase the power of the source of light from 100 to 200, 200 to 300. Here the intensity goes on increasing. As the intensity goes on increasing, the number of electrons emitted per second also increases. Hence, the photocurrent is directly proportional to the intensity of incident radiation. Then, what about second observation here? Effect of applied potential on the photocurrent. Effect of applied potential. Effect of applied potential on the photocurrent. So listen here, photocurrent is also called photoelectric current. This current is due to the photoelectrons which are emitted from the emitter plate, means cathode. Then see here, if we are going to increase the positive potential of the anode, then what happens? The more number of electrons are collected by the anode. If the more number of electrons collected by the anode, then the current in the circuit becomes maximum. So see here, as the potential of anode with respect to cathode increases. Here the anode is at which potential? Positive potential, means as the positive potential of anode with respect to cathode is at negative potential. As the positive potential of anode with respect to cathode increases, the photocurrent also increases. The photocurrent also increases. The photocurrent also increases. See here once again, as the positive potential of the anode increases, ಅಂದರೆ ಆ್ಯನೋಡ್ದ ಪಾಸಿಟಿವ್ ಪೊಟೆನ್ಷಿಯಲನ್ನು ನಾವು ಹೆಚ್ಚಿಗೆ ಮಾಡ್ಕೊತ ಹೋದ್ವಿ ಅಂದರೆ ಇಜೆಕ್ಟ್ ಆದಂಥ ಎಲೆಕ್ಟ್ರಾನ್ಸನ್ನು ಮ್ಯಾಕ್ಸಿಮಮ್ ಎಲೆಕ್ಟ್ರಾನ್ಸನ್ನು ಇದೇನು ಮಾಡುತ್ತಾ ಅಟ್ರಾಕ್ಟ್ ಮಾಡ್ಕೊಳುತ್ತಾ, ಅಂದರೆ ಕಲೆಕ್ಟ್ ಮಾಡ್ಕೊಳುತ್ತಾ. ಅವಾಗ ಕರೆಂಟ್ ಏನಾಗುತ್ತೆ ರೀ ಸರ್ಕ್ಯೂಟ್ನಾಗ ಮ್ಯಾಕ್ಸಿಮಮ್ ಆಗುತ್ತೆ. ಅಂದ್ರೆ ಹೆಂಗೆ ಫೋಟೋ ಕರೆಂಟ್ ಇನ್ಕ್ರೀಸ್ ಮಾಡ್ಬೇಕ್ರಿ ನಾನು? ಬೈ ಇನ್ಕ್ರೀಸಿಂಗ್ ದಿ ಪಾಸಿಟಿವ್ ಪೊಟೆನ್ಷಿಯಲ್ ಆಫ್ ದಿ ಆ್ಯನೋಡ್ ವಿತ್ ರೆಸ್ಪೆಕ್ಟ್ ಟು ದಿ ಕ್ಯಾಥೋಡ್. ಹಿಯರ್ ಆ್ಯನೋಡ್ ಈಸ್ at positive potential, cathode is at negative potential. Okay, so we are going to plot the graph here. Here the frequency must be greater than threshold frequency, means the frequency of incident radiation must be greater than threshold frequency. I will take this one. So graphical representation. See here, then it is origin. Along positive x-axis, positive potential of the anode is taken. Here applied voltage. Along the x-axis we are going to take the applied voltage. Here the voltage is positive, but here the voltage is negative, means the potential of the anode is positive here, but here the potential of the anode is negative. As the positive potential of the anode increases, the photocurrent also increases, because anode collects the more number of ejected electrons from the emitter plate. See here, and when it collects the all electrons which are emitted from the cathode, then the current becomes maximum and it remains constant. That is why this current is called saturation current. ಈ ಕರೆಂಟಿಗೆ ಏನಂತ ಕರಿತೀರಿ ನೀವು? ಸ್ಯಾಚುರೇಷನ್ ಕರೆಂಟ್. ಅಂದರೆ ಕ್ಯಾಥೋಡ್ಲಿಂದ ಎಜೆಕ್ಟ್ ಆದಂಥ ಎಲ್ಲ ಎಲೆಕ್ಟ್ರಾನ್ಸನ್ನು ಆ್ಯನೋಡ್ ಕಲೆಕ್ಟ್ ಮಾಡ್ಕೊತಂದ್ರೆ ಕರೆಂಟ್ ಏನಾಗುತ್ತೆ? ಮ್ಯಾಕ್ಸಿಮಮ್ ಆಗುತ್ತೆ ಮತ್ತು ಕಾನ್ಸ್ಟಂಟ್ ಆಗಿ ಉಳಿಯುತ್ತೆ. ಆ ಕರೆಂಟಿಗೆ ಏನಂತ ಕರಿತೀವಿ ನಾವು? ಸ್ಯಾಚುರೇಷನ್ ಕರೆಂಟ್. If I will change the polarity of the anode, now anode is at positive potential. If the anode is at negative potential, then the anode does not collect the ejected electrons from the cathode because of force of repulsion. See here, it is cathode and it is anode. Cathode is connected to, in first case, negative terminal of the battery, and anode is connected to positive terminal of the battery. So when the anode is connected to positive terminal of the battery, then this anode can collect the ejected electrons from the cathode due to the force of attraction. ಯಾಕಂದ್ರೆ ಆ್ಯನೋಡ್ ಪಾಸಿಟಿವ್ ಪೊಟೆನ್ಷಿಯಲ್ ಐತಿ, ಓಕೆ, ಆ್ಯಂಡ್ ಕ್ಯಾಥೋಡ್ ಏನದ್ರಿ ನೆಗೆಟಿವ್ ಪೊಟೆನ್ಷಿಯಲ್ ಐತಿ. ಇದರಲ್ಲಿಂತ ಇಜೆಕ್ಟ್ ಆದಂಥ ಎಲೆಕ್ಟ್ರಾನನ್ನು ಆ್ಯನೋಡ್ ಏನು ಮಾಡುತ್ತೆ ರೀ? ರಿಸೀವ್ ಮಾಡ್ಕೊಳ್ಳುತ್ತೆ, ಯಾಕಂದ್ರೆ ಫೋರ್ಸ್ ಆಫ್ ಅಟ್ರಾಕ್ಷನ್. ಸೊ ಬಿಕಾಸ್ ಎಲೆಕ್ಟ್ರಾನ್ ಈಸ್ ನೆಗೆಟಿವ್ಲಿ ಚಾರ್ಜ್ಡ್ ಆ್ಯಂಡ್ ಆ್ಯನೋಡ್ ಈಸ್ ಪಾಸಿಟಿವ್, ದೆನ್ ದೇರ್ ಇಸ್ ಅ ಫೋರ್ಸ್ ಆಫ್ ಅಟ್ರಾಕ್ಷನ್ and this electron is collected by the anode, then there is a current. Suppose I will change the polarity of the cathode and anode. Now cathode is connected to positive of the battery and anode is connected to negative of the battery, then it becomes positive and it becomes negative. Then this ejected electron is repelled by the anode, means it does not collected by the anode, hence there is no current in the circuit. So for the negative potential, I will take for the negative potential, the current in the circuit becomes 0. This negative potential is called, negative potential of the anode is called stopping potential, that can be represented by V naught. ಇಲ್ಲಿ ನೋಡ್ರಿ ಇನ್ನೊಂದ್ಸಲ ಕೇಳ್ರಿ, ಆ್ಯನೋಡ್ದು ಪಾಸಿಟಿವ್ ಪೊಟೆನ್ಷಿಯಲನ್ನು ನಾ ಹೆಚ್ಚಿಗೆ ಮಾಡ್ಕೊತ ಹೋದ್ನಿ ಅಂದ್ರೆ ಮೋರ್ ನಂಬರ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಾನ್ಸನ್ನು ಏನು ಮಾಡುತ್ತೆ ಅದು ಕಲೆಕ್ಟ್ ಮಾಡುತ್ತೆ. ಮೋರ್ ನಂಬರ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಕಲೆಕ್ಟ್ ಆದ್ರೆ ಕರೆಂಟ್ ಏನಾಗುತ್ತೆ ರೀ ಮ್ಯಾಕ್ಸಿಮಮ್ ಹಾಕ್ಕೊಂತ ಹೋಗುತ್ತೆ, ಅಂದರೆ ಇನ್ಕ್ರೀಸ್ ಹಾಕ್ಕೊಂತ ಹೋಗುತ್ತೆ. ಎಲ್ಲ ಎಲೆಕ್ಟ್ರಾನ್ಸನ್ನು ಕಲೆಕ್ಟ್ ಮಾಡ್ಕೊತಂದ್ರೆ ಕರೆಂಟ್ ಮ್ಯಾಕ್ಸಿಮಮ್ ಆಗಿ ಕಾನ್ಸ್ಟಂಟ್ ಆಗಿ ಉಳಿಯುತ್ತೆ. ಆ ಕರೆಂಟಿಗೆ ಏನಂತ ಕರಿತೀವಿ ನಾವು, ಸ್ಯಾಚುರೇಷನ್ ಕರೆಂಟ್ ಅಂತ ಕರಿತೀವಿ. ಓಕೆ, ಸಪೋಸ್ ಅದೇ ನಾವು ನೆಗೆಟಿವ್ ಪೊಟೆನ್ಷಿಯಲ್ ಕೊಟ್ಟಿವಿ ಅಂತ ತಿಳ್ಕೊಡ್ರಿ ಆ್ಯನೋಡಿಗೆ. ಸೊ ಅವಾಗ ಏನಾಗುತ್ತೆ ರೀ, ಈ ನೆಗೆಟಿವ್ ಪೊಟೆನ್ಷಿಯಲ್ ಎಲೆಕ್ಟ್ರಾನನ್ನು ಏನು ಮಾಡುತ್ತೆ ರೀ ರಿಪೆಲ್ ಮಾಡೋಕ್ಕೆ ಸ್ಟಾರ್ಟ್ ಮಾಡುತ್ತೆ. ಅಂದ್ರೆ ಈ ಆ್ಯನೋಡ್ ಯಾವುದೇ ಥರ ಎಲೆಕ್ಟ್ರಾನನ್ನು ಕಲೆಕ್ಟ್ ಮಾಡ್ಕೊಳ್ಳಲ್ಲ, ಅಂದ್ರೆ ಕರೆಂಟ್ ಏನಾಯ್ತು ರೀ ಜೀರೋ ಆಗುತ್ತೆ. ಓಕೆ, ಸೊ ಹಿಯರ್ ದಿ ಕರೆಂಟ್ ಬಿಕಮ್ಸ್ ಜೀರೋ. ಐ ವಿಲ್ ಟೇಕ್ ಇಟ್ ಈಸ್ ಫೋಟೋ ಕರೆಂಟ್. Here the intensity and frequency of the incident radiation kept constant. ಇಂಟೆನ್ಸಿಟಿ ಮತ್ತು ಫ್ರೀಕ್ವೆನ್ಸಿ ಎರಡನ್ನೂ ನಾವೇನು ಮಾಡೀವಿ ಕಾನ್ಸ್ಟಂಟಾಗಿ ಇಟ್ಕೊಂಡಿವಿ. ಏನು ವೇರಿ ಮಾಡತ್ತೀರಿ ನಾವು, ವಿ ಆರ್ ಗೋಯಿಂಗ್ ಟು ವೇರಿ ದಿ ಓನ್ಲಿ ದಿ ವೋಲ್ಟೇಜ್ ಆಫ್ ದಿ ಆ್ಯನೋಡ್ ವಿತ್ ರೆಸ್ಪೆಕ್ಟ್ ಟು ದಿ ಕ್ಯಾಥೋಡ್. ಓಕೆ, ಸೊ ದಿಸ್ ಈಸ್ ಅಬೌಟ್ ದಿ ಸೆಕೆಂಡ್ ಅಬ್ಸರ್ವೇಷನ್. ಸೊ ವಾಟ್ ಅಬೌಟ್ ಥರ್ಡ್ ಅಬ್ಸರ್ವೇಷನ್? So before that we have to know what do you mean by stopping potential. This is one mark question. Define stopping potential. Stopping potential is also called cutoff potential. Then what do you mean by stopping potential? It is the minimum negative potential of the anode for which the current in the circuit becomes zero. It is the minimum negative potential. It is the minimum negative potential given to the anode. Negative potential given to the anode for which, for this minimum negative potential, the current in the circuit becomes zero, because there is no electron collected by the anode. If there is no electron collected by the anode, then there is no current in the circuit. Then the current read by the ammeter is zero, for which the current in the circuit becomes zero. The current in the circuit becomes zero. And this can be represented by V naught. So stopping potential is represented by V naught. Okay. Stopping potential is nothing but it is a negative potential applied to the anode to make the current in the circuit is zero. Then what do you mean by saturation current? It is the maximum current in this circuit for the fixed frequency and fixed intensity. Frequency constant ಮತ್ತು intensity constant ಇಟ್ಕೊಂಡಾಗ ಒಂದು ಮ್ಯಾಕ್ಸಿಮಮ್ ಕರೆಂಟ್ ಪ್ರೊಡ್ಯೂಸ್ ಆಗುತ್ತೆ ರೀ. ಆ ಮ್ಯಾಕ್ಸಿಮಮ್ ಕರೆಂಟಿಗೆ ನಾವೇನಂತ ಕರಿತೀವಿ, ಸ್ಯಾಚುರೇಷನ್ ಕರೆಂಟ್. ದೆನ್ ವಾಟ್ ಯು ಮೀನ್ ಬೈ ಸ್ಯಾಚುರೇಷನ್ ಕರೆಂಟ್? It is the maximum current. It is the maximum current. When there is a maximum current, when the anode collects all the electrons ejected out from the cathode, then the current in the circuit becomes maximum and it remains constant. That current is called saturation current. It is the maximum current in the circuit for the fixed frequency. How to fix the frequency here? Frequency na constant ಆಗಿ ಹೆಂಗೆ ಇಟ್ಕೋಬೇಕ್ರಿ? ಬೈ ಯೂಸಿಂಗ್ ಅ ಕಲರ್, ಮೀನ್ಸ್ ಅ ಕಾನ್ಸ್ಟಂಟ್ ಕಲರ್. ಒಂದೇ ಕಲರ್ ಯೂಸ್ ಮಾಡ್ಕೊತ ಹೋಗ್ಬೇಕ್ರಿ, ಅಂದ್ರೆ ಫ್ರೀಕ್ವೆನ್ಸಿ ಕಾನ್ಸ್ಟಂಟ್ ಆಗಿರುತ್ತೆ. ಓಕೆ, ಸೊ ಫಾರ್ ದಿ ಫಿಕ್ಸ್ಡ್ ಫ್ರೀಕ್ವೆನ್ಸಿ and how to fix the intensity here? By taking the constant power rating source of light and fixed intensity. ಇಂಟೆನ್ಸಿಟಿ ವೇರಿ ಮಾಡ್ಬೇಕಂದ್ರೆ ಆ ಸೋರ್ಸ್ ಆಫ್ ಲೈಟಿದ್ದು ಪವರ್ ರೇಟಿಂಗ್ ವೇರಿ ಮಾಡ್ಕೊತ ಹೋಗ್ಬೇಕ್ರಿ ಬೈ ಯೂಸಿಂಗ್ ರೆಗ್ಯುಲೇಟರ್. ಬಟ್ ಇಂಟೆನ್ಸಿಟಿ ಕಾನ್ಸ್ಟೆಂಟ್ ಆಗಿ ಇಟ್ಕೊಬೇಕಂತಂದ್ರೆ ನಾವು ಪವರ್ ರೇಟಿಂಗನ್ನು ವೇರಿ ಮಾಡೋಕೆ ಹೋಗ್ಬಾರ್ದು, ಪವರ್ ರೇಟಿಂಗ್ ಕಾನ್ಸ್ಟೆಂಟ್ ಆಗಿ ಇಟ್ಕೋಬೇಕು. ಇಂಟೆನ್ಸಿಟಿ ಕಾನ್ಸ್ಟೆಂಟ್ ಉಳಿತು ಮತ್ತು ಸೇಮ್ ಕಲರ್ ರೇಡಿಯೇಷನನ್ನು ಯೂಸ್ ಮಾಡಿದ್ದೀವಿ ಅಂತಂದ್ರೆ ಫ್ರೀಕ್ವೆನ್ಸಿನೂ ಕಾನ್ಸ್ಟೆಂಟ್ ಆಗಿ ಉಳಿಯುತ್ತೆ. ದೆನ್ ಏನು ವೇರಿ ಮಾಡ್ಬೇಕ್ರಿ ಇಲ್ಲಿ ನಾವು ಜಸ್ಟ್ ವಿ ಆರ್ ಗೋಯಿಂಗ್ ಟು ವೇರಿ ದಿ potential only, potential of the anode with respect to the cathode. Then next one, effect of frequency of incident radiation on the kinetic energy of ejected electrons. Third one, effect of frequency of incident radiation on kinetic energy of photoelectrons. See here, this is very important. As the frequency of incident radiation increases, the kinetic energy of ejected electrons also increases. ಫ್ರೀಕ್ವೆನ್ಸಿ ಹೆಚ್ಚಿಗೆ ಮಾಡ್ಕೊತ ಹೋದ್ವಿ ಅಂತ ತಿಳ್ಕೊಡ್ರಿ, ಇಜೆಕ್ಟ್ ಆದಂಥ ಎಲೆಕ್ಟ್ರಾನ್ದು ಕೈನೆಟಿಕ್ ಎನರ್ಜಿನೂ ಏನಾಗುತ್ತೆ ರೀ ಹೆಚ್ಚಾಕೊಂತ ಹೋಗುತ್ತೆ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಸಿ ಹಿಯರ್, by the Einstein's photoelectric equation, we will discuss about Einstein's photoelectric equation in next class. So ಅದೇ equation ಯೂಸ್ ಮಾಡಿಕೊಂಡು ಈಗ ನಾವು ಡಿಸ್ಕಸ್ ಮಾಡೋಣ ರೀ. ದೆನ್ what is Einstein's photoelectric equation? E is equal to phi naught plus Ke, K maximum. What do you mean by K maximum here? It is the maximum kinetic energy of the ejected electron from the emitter plate. Then what is phi naught here? Work function of the emitter plate. Okay. And what is E here? E is nothing but energy of incident radiation. Energy of incident radiation can be written as h nu, h into nu. Energy of incident radiation is equal to h into nu. And what is the work function of the metal? That is pi naught, that is h into nu naught. Then plus kinetic energy of the ejected electron. See here, if we are going to increase the frequency of incident radiation, then what happens? The energy of incident radiation increases. As the energy of incident radiation increases, part of this energy ejects the electron from the surface of the metal, and remaining part of energy is converted into the kinetic energy of the ejected electron. Here noಡ್ರಿ, let us take cesium metal. Then what is the minimum energy required to eject an electron from the surface of the cesium metal? That is 2.14 electron volt. That is equal to work function. ಅದಕ್ಕೆ ಏನಂತ ಕರಿತೀವಿ ನಾವು? ವರ್ಕ್ ಫಂಕ್ಷನ್. If the energy of incident radiation is equal to the work function of the metal, the electron is just escaped from the surface of the metal, but it will not move. Electron metal surface ಲಿಂದ ಹೊರಗಡೆ ಬರುತ್ತೆ, ಬಟ್ ಇದು ಮೂವ್ ಆಗಲ್ಲ. ಯಾಕಂದ್ರೆ ಎನರ್ಜಿ ಆಫ್ ಇನ್ಸಿಡೆಂಟ್ ರೇಡಿಯೇಷನ್ ಎದಕ್ಕೆ ಈಕ್ವಲ್ ಐತ್ರಿ? ದಟ್ ಈಸ್ ಈಕ್ವಲ್ ಟು ವರ್ಕ್ ಫಂಕ್ಷನ್ ಆಫ್ ದಿ ಮೆಟಲ್. ಸಿ ಹಿಯರ್, if h nu and h nu naught are both are equal, I will take h nu naught to the left hand side. H nu is nothing but it is a energy of incident radiation. H nu naught is nothing but it is a work function of the metal, and that is equal to kinetic energy of the ejected electron. Then if the energy of incident radiation and work function both are equal, means E is equal to pi naught. Then what happens here? This one becomes 0. Okay. ಎನರ್ಜಿ ಏನು ಇನ್ಸಿಡೆಂಟ್ ಮಾಡಿರ್ತೀರಲ್ರಿ ಅದು 2.14 ಆಗಿತ್ತು, ಇದ್ರದ್ದು ವರ್ಕ್ ಫಂಕ್ಷನು 2.14 ಆಗಿತ್ತಂದ್ರೆ ಎಲೆಕ್ಟ್ರಾನ್ ಜಸ್ಟ್ ಎಸ್ಕೇಪ್ ಆಗುತ್ತೆ ರೀ, ಬಟ್ ಅದು ಮೂವ್ ಆಗಲ್ಲ. ಅಂದ್ರೆ ಕೈನೆಟಿಕ್ ಎನರ್ಜಿ ಏನಾಯ್ತು ರೀ? 0 ಆಗುತ್ತೆ. Hence the kinetic energy becomes 0 only when the energy of incident radiation is equal to work function of the metal. If the energy of incident radiation is greater than work function of the metal, then what happens? I will take supposed to be 3.14 electron volt. 3.14 electron volt. So what is the minimum energy required to eject an electron from the surface of the cesium metal? That is 2.14 electron volt. Then what about remaining energy? Remaining energy is 1 electron volt. That 1 electron volt is converted into kinetic energy of the ejected electron. See here, h nu is nothing but energy of incident radiation, and h nu naught is work function of the metal plus K maximum. K maximum is nothing but it is a kinetic energy of ejected electron from the emitter plate. Then here what about energy of incident radiation? 3.14 electron volt. It is greater than work function of the metal. ನಾವು ಏನು ರೇಡಿಯೇಷನ್ ಇನ್ಸಿಡೆಂಟ್ ಮಾಡಿರ್ತೀವಲ್ರಿ ಅದ್ರದ್ದು ಎನರ್ಜಿ ವರ್ಕ್ ಫಂಕ್ಷನ್ಕಿಂತ ಏನಿರಬೇಕು, ಜಾಸ್ತಿ ಇರಬೇಕು ಅಥವಾ ಈಕ್ವಲ್ ಆಗಿತ್ತಂದ್ರೆ ಅಷ್ಟೇ ಎಲೆಕ್ಟ್ರಾನ್ ಇಜೆಕ್ಟ್ ಆಗುತ್ತೆ. ಅದಕ್ಕಿಂತ ಕಡಿಮೆ ಇತ್ತಂದ್ರೆ ದೇರ್ ಇಸ್ ನೋ ಇಜೆಕ್ಷನ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಾನ್ ಫ್ರಮ್ ದಿ ಸರ್ಫೇಸ್ ಆಫ್ ದಿ ಮೆಟಲ್. Here the energy of incident radiation is 3.14, but what is the work function of the cesium metal? That is 2.14. Then what is the kinetic energy of the emitted electron from the cesium metal? That is 3.14 minus 2.14. 3.14 minus 2.14, that is 1 electron volt. Okay. How to increase the energy of incident radiation? By increasing the frequency of incident radiation. As the frequency of incident radiation increases, the kinetic energy of the ejected electron also increases. So I will take one more example. If the energy of incident radiation is equal to 4.14 electron volt. So here part of energy required to eject the electron from the surface of the metal, remaining part of energy is converted into kinetic energy of ejected electron. Here nodri. So kinetic energy of the ejected electron is equal to energy of incident radiation minus work function of the metal. So what is the energy of incident radiation here? 4.14, which is greater than work function of the cesium metal. We are going to take the example is cesium metal. 4.14 minus, then what is the minimum energy required to eject an electron from the cesium metal? That is 2.14. Then subtracting them, we will get 2 electron volt. Then what is the kinetic energy of the ejected electron? That is 2 electron volt. So see here, as the energy of incident radiation increases, then the kinetic energy of the ejected electron also increases. How to increase the energy of incident radiation? By increasing the frequency. Frequency increase ಮಾಡ್ಕೊಂತ ಹೋಗ್ರಿ, because energy of incident radiation is equal to h into nu. Then energy is directly proportional to frequency of incident radiation. As the frequency of incident radiation increases, energy of incident radiation also increases. As the energy of incident radiation increases, then the kinetic energy of the ejected electron also increases. That means what we concluded from this example. ಈ ಎಕ್ಸಾಂಪಲ್ ಇಂದ ನಾವು ಏನು ಕನ್ಕ್ಲೂಷನ್ ಹೇಳ್ತೀವಿ ರೀ? As the frequency of incident radiation increases, as the frequency of incident radiation increases, if we are going to increase the frequency of incident radiation, then the energy of incident radiation also increases, because E is equal to h into nu. Then as the frequency of incident radiation increases, the kinetic energy of ejected electron increases. Ejected means here emitted electron. Ejected electron increases. So let us plot the graph here. But here the frequency for the photoelectric emission, the frequency of the incident radiation must be equal to the threshold frequency or greater than threshold frequency, but not less than threshold frequency. If it is less than threshold frequency, there is no photoelectric emission takes place. Once again let us consider example cesium metal. We are going to remove an electron from the surface of the cesium metal. How much energy we have to give? Minimum energy, that is 2.14, but I will give 2 electron volt. 2.14 ಕೊಡಬೇಕ್ರಿ ನಾನು. 2.14 ಕೊಡಬೇಕಂದ್ರೆ ಫ್ರೀಕ್ವೆನ್ಸಿ ಎಷ್ಟಿತ್ತು ರೀ? ದಟ್ ಈಸ್ 5.16 into 10 to the power of 14 hertz ಇತ್ತು. 2.14 ಎನರ್ಜಿ ಕೊಟ್ಟರೆ frequency of incident radiation ಎಷ್ಟಿರ್ಬೇಕ್ರಿ 5.16. But how much energy is given to the surface of the cesium metal? Only 2 electron volt. Means here the frequency is less than threshold frequency. There is no ejection of electron from the surface of the metal. If there is no ejection of electron from the surface of the metal, then there is no photoelectric emission. ಇಲ್ಲಿ ನೋಡ್ರಿ, ಯಾವಾಗಲೂ ಒಂದು ಮೆಟಲಿಂದ ಎಲೆಕ್ಟ್ರಾನ್ ಇಜೆಕ್ಟ್ ಆಗ್ಬೇಕಂದ್ರೆ ಆ ಇನ್ಸಿಡೆಂಟ್ ರೇಡಿಯೇಷನ್ ಫ್ರೀಕ್ವೆನ್ಸಿ ಥ್ರೆಶೋಲ್ಡ್ ಫ್ರೀಕ್ವೆನ್ಸಿಗೆ ಈಕ್ವಲರ್ ಆಗಿರ್ಬೇಕು, ಅದಕ್ಕಿಂತ ಹೆಚ್ಚಾಗಿರ್ಬೇಕು, ಬಟ್ ಅದಕ್ಕಿಂತ ಕಡಿಮೆ ಇರಬಾರ್ದು. ಓಕೆ, as the frequency of incident radiation increases, the kinetic energy of ejected electron also increases. Let us plot the graph here. Now, along x-axis I will take frequency of incident radiation, and along y-axis I will take kinetic energy of the ejected electron, means kinetic energy of photoelectron. Then for a metal, for a given metal, for example cesium metal, what is threshold frequency? I will take nu1. It is a minimum frequency required to eject an electron. Below this frequency there is no ejection of electron from the metal. If there is no ejection of electron from the metal, then there is no kinetic energy. Kinetic energy is negative. Suppose if the frequency of incident radiation goes on increasing from its threshold frequency, the kinetic energy of photoelectron also increases. This is for the metal 1. I will take, for example, it is a cesium metal. Suppose I will take another metal, for example zinc. For the zinc metal, what is the minimum frequency required? That is 10.44 into 10 to the power of 14 Hertz. Here visible light is required, but here UV radiation is required for the ejection of electron from the cesium metal. If the frequency of incident radiation is greater than this frequency, then the kinetic energy of photoelectron goes on increases. Then this is for the metal 2. I took here two metals, metal 1 and metal 2. Then it is a graphical representation of the relation between frequency of incident radiation and kinetic energy of the ejected electron. Then if the energy of incident radiation is less than work function, what happens? The kinetic energy becomes negative. Energy never be negative here, because kinetic energy never be negative. If the kinetic energy is negative, then the photoelectric emission is not possible. See here, E is equal to, E andre enri energy of incident radiation. This is called Einstein's photoelectric equation. We will discuss what is Einstein's photoelectric equation in next class. Okay, E is equal to pi naught plus kinetic energy of ejected electron, maximum kinetic energy of ejected electron. ನಾವು ಕೊಟ್ಟಂಥ ಎನರ್ಜಿ ರೀ ಒಳಗಡೆ ರೀ, ಆ ಎನರ್ಜಿ ಎರಡು ಪಾರ್ಟ್ ಆಗಿ ಡಿವೈಡ್ ಆಗುತ್ತೆ. ಒಂದಿಷ್ಟು ಪಾರ್ಟ್ ಏನಿರುತ್ತೆ ಅಂದ್ರೆ ಆ ಎಲೆಕ್ಟ್ರಾನನ್ನು ಇಜೆಕ್ಟ್ ಮಾಡುತ್ತೆ, ಇನ್ನೊಂದು ಪಾರ್ಟ್ ಏನಾಗಿರುತ್ತೆ ರೀ ಆ ಎಲೆಕ್ಟ್ರಾನ್ದು ಕೈನೆಟಿಕ್ ಎನರ್ಜಿ ಆಗಿ ಕನ್ವರ್ಟ್ ಆಗಿರುತ್ತೆ. ಓಕೆ, ಸೊ ಸಿ ಹಿಯರ್ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಐ ವಿಲ್ ಟೇಕ್ ಅಗೇನ್ cesium metal. What is the minimum energy required to eject an electron from the cesium metal? 2.14 electron volt. Okay, 2.14 electron volt idre okay ರೀ. But if it is less than 2.14 electron volt, there is no emission of electron from the cesium metal takes place. Suppose I will take it is 2. Then what is the work function of cesium metal? See here, we are going to take the example is cesium. Then work function, minimum energy required to eject an electron from the cesium metal, that is 2.14, but the given energy is how much? 2 electron volt. Then the what is the kinetic energy of emitted electron? That is 2 minus, I will take this one to the left hand side, that is 2 minus 2.14, that is minus of 0.14 electron volt. Here kinetic energy is negative, so kinetic energy is negative means here photoelectric emission is not possible, because the kinetic energy never be negative. Kinetic energy ಯಾವಾಗಲೂ ಏನಾಗಿರಲ್ಲ ರೀ, ನೆಗೆಟಿವ್ ಆಗಿರಲ್ಲ. ಓಕೆ, now fourth observation is the effect of frequency of incident radiation on the stopping potential of the anode. Effect of frequency of incident radiation. effect of frequency of incident radiation on the stopping potential of anode. Means here how the frequency of incident radiation depends on the stopping potential of anode. What do you mean by stopping potential? It is a minimum negative potential given to the anode to make the current in the circuit zero. ಈಗ ನಾವು ಆ್ಯನೋಡಿಗೆ ನೆಗೆಟಿವ್ ಪೊಟೆನ್ಷಿಯಲ್ ಕೊಟ್ಟಿವಿ ಅಂತ ತಿಳ್ಕೊಡ್ರಿ, ಕ್ಯಾಥೋಡ್ಲಿಂದ ಇಜೆಕ್ಟ್ ಆದಂಥ ಎಲೆಕ್ಟ್ರಾನನ್ನು ಅದು ಕಲೆಕ್ಟ್ ಮಾಡಲ್ಲ, ಯಾಕಂದ್ರೆ ರಿಪಲ್ಸಿವ್ ಫೋರ್ಸ್ ಇರುತ್ತೆ. ಓಕೆ, ಸೊ ಆ ಮಿನಿಮಮ್ ನೆಗೆಟಿವ್ ಪೊಟೆನ್ಷಿಯಲ್ಗೆ ಏನಂತ ಕರಿತೀವಿ ನಾವು? ಸ್ಟಾಪಿಂಗ್ ಪೊಟೆನ್ಷಿಯಲ್ ಅಂತ ಕರಿತೀವಿ. Then effect of frequency of incident radiation on the stopping potential of anode. See here, as the frequency of incident radiation increases, the kinetic energy of ejected electron increases. Einstein's photoelectric equation ಏನು ಹೇಳ್ತೀರಿ? H into nu. H into nu means here it is the energy of incident radiation. H into nu naught, it is work function of the metal. ಅದು ಯಾವ ಮೆಟಲ್ ಇರುತ್ತೆ ಅದ್ರದ್ದು ವರ್ಕ್ ಫಂಕ್ಷನ್ ರೀ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಸಿಜಿಎಮ್ ಮೆಟಲ್ ಇತ್ತಂದ್ರೆ 2.14, ಜಿಂಕ್ ಮೆಟಲ್ ಇತ್ತಂದ್ರೆ ರೀ 4.33 ಎಲೆಕ್ಟ್ರಾನ್ ವೋಲ್ಟ್ ಇರುತ್ತೆ. ಡಿಪೆಂಡಿಂಗ್ ಆನ್ ದಿ ಮೆಟಲ್ ವರ್ಕ್ ಫಂಕ್ಷನ್ ಇಸ್ ದೇರ್. Then plus kinetic energy 1/2m V maximum square. So V maximum square, V maximum means here it is the maximum velocity of the ejected electron. Then H nu minus nu naught, because I will take nu naught, H nu naught to the left hand side. In both what is common? H is common. Then it is kinetic energy of the ejected electron. See here, I will take H taken to the, sorry, I will take H to the right hand side. Nu minus nu naught is equal to kinetic energy of the ejected electron divided by Planck's constant. That means nu minus nu naught is directly proportional to the kinetic energy of the ejected electron, because H is constant, Planck's constant. Okay, then as the frequency of incident radiation increases, the kinetic energy of the ejected electron also increases. ಈಗ ನೋಡ್ರಿ, ಇದು ಈ ಫ್ರೀಕ್ವೆನ್ಸಿ ಫಿಕ್ಸ್ಡ್ ಇರುತ್ತೆ ರೀ, ಅಂದ್ರೆ ರೀ ಮಿನಿಮಮ್ ಫ್ರೀಕ್ವೆನ್ಸಿ, ದಟ್ ಈಸ್ ಕಾಲ್ಡ್ ಥ್ರೆಶೋಲ್ಡ್ ಫ್ರೀಕ್ವೆನ್ಸಿ. ಫಾರ್ ದಿ ಗಿವನ್ ಮೆಟಲ್ ಇಟ್ ಈಸ್ ಫಿಕ್ಸ್ಡ್, ಬಟ್ ವಾಟ್ ವಿ ಆರ್ ಗೋಯಿಂಗ್ ಟು ಚೇಂಜ್ ಹಿಯರ್ ದಿ ಫ್ರೀಕ್ವೆನ್ಸಿ ಆಫ್ ಇನ್ಸಿಡೆಂಟ್ ರೇಡಿಯೇಷನ್. ಅಂದರೆ ಫ್ರೀಕ್ವೆನ್ಸಿ ಆಫ್ ಇನ್ಸಿಡೆಂಟ್ ರೇಡಿಯೇಷನನ್ನು ಹೆಚ್ಚಿಗೆ ಮಾಡ್ಕೊತ ಹೋಗ್ತೀನಿ. ಅದ್ರ ಒಳಗಡೆ ರೀ ಆ ಫ್ರೀಕ್ವೆನ್ಸಿ ಒಳಗಡೆ ಒಂದಿಷ್ಟು ಫ್ರೀಕ್ವೆನ್ಸಿ ಎಲೆಕ್ಟ್ರಾನನ್ನು ಇಜೆಕ್ಟ್ ಮಾಡುತ್ತಾ, ಅದು ಫಿಕ್ಸ್ಡ್ ಆಗಿರುತ್ತೆ, ದಟ್ ಈಸ್ ನ್ಯೂ ನಾಟ್. ದೆನ್ ರಿಮೈನಿಂಗ್ ಏನಾಗಿರುತ್ತೆ ಅಂದ್ರೆ ಅದು ಕೈನೆಟಿಕ್ ಎನರ್ಜಿಯಾಗಿ ಕನ್ವರ್ಟ್ ಆಗಿರುತ್ತೆ. ಇಜೆಕ್ಟ್ ಆದಂಥ ಎಲೆಕ್ಟ್ರಾನ್ ಏನಾಗಿ ಕನ್ವರ್ಟ್ ಆಗಿರುತ್ತೆ ರೀ? ಕೈನೆಟಿಕ್ ಎನರ್ಜಿಯಾಗಿ ಕನ್ವರ್ಟ್ ಆಗಿರುತ್ತೆ. ಓಕೆ, ಅಂದರೆ ಫ್ರೀಕ್ವೆನ್ಸಿ ಆಫ್ ಇನ್ಸಿಡೆಂಟ್ ರೇಡಿಯೇಷನನ್ನು ನಾವು ಹೆಚ್ಚಿಗೆ ಮಾಡ್ಕೊತ ಹೋದಿವಿ ಅಂತಂದ್ರೆ ಕೈನೆಟಿಕ್ ಎನರ್ಜಿ ಆಫ್ ಇಜೆಕ್ಟೆಡ್ ಎಲೆಕ್ಟ್ರಾನ್ ಏನಾಗುತ್ತೆ ರೀ? ಇಲ್ಲಿ ಹೆಚ್ಚಾಗ್ಕೊತ ಹೋಗುತ್ತೆ. ಮೀನ್ಸ್ the frequency of incident radiation is directly proportional to the kinetic energy of ejected electron. Then if the kinetic energy of the ejected electron is maximum, we require maximum negative potential to stop the electron here, because the electrons moving with high speed, electrons high speed ಲಿಂದ ಮೂವ್ ಆಗುತ್ತಾವ ಅಂತಂದ್ರೆ ಅದನ್ನು ಸ್ಟಾಪ್ ಮಾಡ್ಬೇಕಂದ್ರೆ ನಾವು ಮ್ಯಾಕ್ಸಿಮಮ್ ನೆಗೆಟಿವ್ ಪೊಟೆನ್ಷಿಯಲ್ ಕೊಡ್ಬೇಕ್ರಿ ಅದಕ್ಕೆ ಆ್ಯನೋಡ್ಗೆ. ಅಂದ್ರೆ ರೀ ಫ್ರೀಕ್ವೆನ್ಸಿ ಹೆಚ್ಚಿತ್ತಂದ್ರೆ ಕೈನೆಟಿಕ್ ಎನರ್ಜಿ ಹೆಚ್ಚಾಯ್ತು, ಕೈನೆಟಿಕ್ ಎನರ್ಜಿ ಹೆಚ್ಚಿತ್ತಂದ್ರೆ ನಾವು ಮ್ಯಾಕ್ಸಿಮಮ್ ನೆಗೆಟಿವ್ ಪೊಟೆನ್ಷಿಯಲನ್ನು ಎದಕ್ಕೆ ಕೊಡ್ಬೇಕ್ರಿ? ಆ್ಯನೋಡಿಗೆ ಕೊಡ್ಬೇಕು. ಅಂದ್ರೆ ಸ್ಟಾಪಿಂಗ್ ಪೊಟೆನ್ಷಿಯಲನ್ನು ಹೆಚ್ಚಿಗೆ ಮಾಡ್ಕೊತ ಹೋಗ್ಬೇಕು. ಅಂದ್ರೆ ಇದ್ರ ಅರ್ಥ ಏನು ರೀ? ಆ್ಯಸ್ ದಿ ಫ್ರೀಕ್ವೆನ್ಸಿ ಆಫ್ ಇನ್ಸಿಡೆಂಟ್ ರೇಡಿಯೇಷನ್ ಇನ್ಕ್ರೀಸಸ್, ದಿ ಕೈನೆಟಿಕ್ ಎನರ್ಜಿ ಆಫ್ ದಿ ಇಜೆಕ್ಟೆಡ್ ಎಲೆಕ್ಟ್ರಾನ್ ಆಲ್ಸೋ ಇನ್ಕ್ರೀಸಸ್. ಆ್ಯಸ್ ದಿ ಕೈನೆಟಿಕ್ ಎನರ್ಜಿ ಆಫ್ ದಿ ಇಜೆಕ್ಟೆಡ್ ಎಲೆಕ್ಟ್ರಾನ್ ಇನ್ಕ್ರೀಸಸ್, so to stop those electrons, means ejected electrons, we have to increase the stopping potential of the anode. Means the frequency of incident radiation is directly proportional to the stopping potential. Edike equal agirutte ರೀ? Stopping potential. And this frequency is directly proportional to kinetic energy, kinetic energy of the ejected electron. Then kinetic energy is directly proportional to the stopping potential given to the anode to stop the fast moving electrons, because to make the current in the circuit zero. Then we have to remove this proportionality by applying constant, that is E into V naught. What is E here? E is nothing but charge on electron, charge on an electron. Then it is the formula for the relation between kinetic energy of ejected electron and stopping potential, and how the stopping potential is related to frequency directly. Okay, see here, as the frequency of incident radiation increases, kinetic energy of the ejected electron increases. As the kinetic energy of the ejected electron increases, we have to increase the stopping potential of the anode, because to stop the fast moving electrons. ಫಾಸ್ಟ್ ಮೂವಿಂಗ್ ಎಲೆಕ್ಟ್ರಾನ್ಸನ್ನು ಸ್ಟಾಪ್ ಮಾಡ್ಬೇಕಾಯ್ತಂದ್ರೆ ನಾವು ಸ್ಟಾಪಿಂಗ್ ಪೊಟೆನ್ಷಿಯಲನ್ನು ಏನು ಮಾಡ್ಬೇಕು ರೀ, ಹೆಚ್ಚು ಮಾಡ್ಕೊತ ಹೋಗ್ಬೇಕು. ಇದು ನಮಗೆ ಮೇನ್ ಇಂಪಾರ್ಟೆಂಟ್ ರೀ. ಸೊ ವಿ ಆರ್ ಗೋಯಿಂಗ್ ಟು ರೀಪ್ರೆಸೆಂಟ್ ದಿಸ್ ಒನ್ ಬೈ ಗ್ರಾಫಿಕಲಿ. This side I will take positive potential of the anode, and this side I will take negative potential of the anode, and it is a applied voltage. Along x-axis, what is taken here? Applied voltage. Then let us take, it is a photo current. Along y-axis I will take photo current. Then I will take two frequencies here. One frequency is nu2 and another frequency is nu1. If the frequency nu2 is greater than nu1, then for which frequency we required maximum stopping potential? That is for nu2. Frequency more means we required maximum stopping potential. Then this is for nu2, and this is the stopping potential for the frequency of incident radiation, that is nu2, and this is the stopping potential for the frequency nu1, because we required minimum stopping potential for nu1 and we required maximum stopping potential for nu2. Then but there is a saturation current. If the voltage applied across the anode is positive and the current becomes maximum, that is called saturation current. So this is the graphical representation of the effect of frequency of incident radiation on the stopping potential of the anode. See here once again, if the frequency is maximum, we required maximum stopping potential. If the frequency is minimum, we required minimum stopping potential. Okay, so this is about the experimental observations on photoelectric effect.